Welcome to another video in our series of videos looking at the solutions to the second in-course exam for Math0100, preliminary Math 1. So we're looking at question 3. And question 3 basically involves evaluating limits as x approaches certain values. Also to check if a given function is continuous at a particular value of x, and also involve differentiating from first principles. So we'll start with part 1 of part A, which wants us to evaluate the limit of x squared plus x minus 2 all over x squared minus 1 as x approaches minus 1. So we have lim x approaches minus 1 of x squared plus x minus 2 all over x squared minus 1. Now usually when we have rational functions like these, we often try direct substitution first to see what it actually gives us. So let's try direct substitution. So by direct substitution, so we're going to substitute the value minus 1 into the given function. Substitution. We get minus 1 squared minus 1 minus 2 all over minus 1 squared minus 1, which gives 1 minus 1 minus 2 divided by 1 minus 1. 1 minus 1 is 0, so this gives us minus 2 over 0. Now, 0, whenever 0 is in the denominator of any fraction, we normally say it is undefined. But there's another way of saying it is infinite. And because it's basically minus 2 over 0, we would be tempted to say it's basically minus infinity. That is what we'd be tempted to say. It is minus infinity. But however, before we actually jump to this conclusion, we'll try to simplify the expression first and then see what that gives us. So let's examine the function x squared plus x minus 2 divided by x squared minus 1. Now let's look at the denominator, x squared minus 1. We should be able to recognize this as a difference of two squares. X squared, 1 is also a squared number, so x squared minus 1, that would be x minus 1 times x plus 1. The numerator is also a quadratic, and we'll check if it can be factorized. And it happens to be able to be factorized. When we factorize x squared plus x minus 2, what we get is x minus 1 times x plus 2. So when we factorize x squared plus x minus 2, we get x minus 1 times x minus 2. Now what do we notice? We have an x minus 1 factor in the numerator, and we also have an x minus 1 factor in the denominator, so we could actually go ahead and we can cancel these. So therefore this becomes lim as x approaches minus 1 of x plus 2 divided by x plus 1. And then of course we substitute x equals minus 1, which gives us minus 1 plus 2 over minus 1 plus 1, which gives us 1 over 0, which we say is equal to infinity. So what this basically shows is that as x approaches negative 1, the function actually approaches infinity, right? Now, another way you can actually check how true this is, you can actually take turns in substituting a value of x very close to minus 1 and see what that value gives to the function. Now, I will leave you to do that. So for instance, suppose you could try substituting something like x equals minus 0.99999, and of course you could keep on getting close to minus 1 and see what value this function approaches as x approaches minus 1. So that is one way to actually check if it is actually getting very, very large, that is approaching infinity as x approaches minus 1. So that was part 1. Now let's examine part 2. Part 2 wants us to evaluate limits as x approaches 4 of 2 minus root x all over 4 minus x. So again, we'll try direct substitution first. So by direct substitution, so direct substitution gives 2 minus root of 4 divided by 4 minus 4. So whenever we see the root of a number under these circumstances, we often are only interested in the positive square root. So root of 4 would be equal to 2 in this case, despite knowing that root of 4 could also be minus 2. But now we're only interested in the positive square root, so this becomes 2 minus 2 over 4 minus 4, which is equal to 0 over 0. Now, whenever we end up with 0 over 0 by direct substitution, we say that this is indeterminate. So this is indeterminate and therefore we must find another way, or we must find a way to simplify the given function before we directly substitute the value of x, which is equal to 4. Now, many times when students have to deal with limits involving a radical or a square root, then what they normally do is to multiply both numerator and denominator by the conjugate of the term involving the square root. So this term is 2 minus root x. The conjugate of this is 2 plus root x. But that is not always the correct approach. In this particular question, we must try to identify that there is a link between 2 minus root x and 4 minus x. As a matter of fact, in a previous question, we're able to recognize x squared minus 1 as a difference of 2 squares. However, if we examine 4 minus x carefully and compare to 2 minus root x, we'll also see that this also can be considered to be the difference of 2 squares. So what we get is this: 2 minus root x all over, if you write it like this, 2 squared minus root x squared. Then this essentially is the difference of 2 squares. So this basically gives us 2 minus root x all over 2 minus root x times 2 plus root x. And our 2 minus root x terms in the numerator and the denominator will cancel. So that cancels that, which leaves us with 1 over 2 plus root x. And essentially our limit becomes lim as x approaches 4 of 1 over 2 plus root x, which gives us 1 over 2 plus root 4, which is equal to 1 over 2 plus 2, which is equal to a quarter. So as x approaches 4, this function 2 minus root x all over 4 minus x approaches a quarter. Now let's do part 3. So part 3 involves limit to infinity. So lim x approaches infinity of 3x to the 4th plus 3x squared plus x minus 2 all over x to the 4th minus 1. Now we look at this question using different approaches. In the first approach, what we're going to do is we're going to consider how these individual terms behave as x gets very, very large, that is, as x approaches infinity. Now let's look at the numerator. In the numerator, we have 3x to the 4th plus 3x squared plus x minus 2. Now what happens to each of these terms as x gets very, very large, as approaches infinity? As x gets very large, that is, approaches infinity, x to the 4th will grow much faster than x squared. Likewise, it will grow much, much faster than x. And of course, the minus 2 becomes insignificant. So as x approaches infinity, essentially, this term, 3x to the 4th, becomes a dominant term in the numerator. So we can basically rewrite. So this essentially becomes lim x approaches infinity of 3x to the 4th in the numerator, right? So again, as x gets very large, that is, approaches infinity, x to the 4th will grow much, much faster than x squared, and as a result, 3x to the 4th becomes the dominant term of the numerator. Now let's examine the denominator. In the denominator, we have x to the 4th minus 1. Now as x gets very large, approaches infinity, then x to the 4th gets much larger than minus 1, and so this minus 1 essentially becomes insignificant. So again, now the dominant term in the denominator is x to the fourth. So this entire thing becomes lim as x approaches infinity of 3x to the fourth divided by x to the fourth. Now we have 3x to the fourth divided by x to the fourth, which of course we can actually simplify. So that will cancel that, which leaves us with lim x approaches infinity of 3. Now 3 is just a constant, which is of course independent of x, and so is not affected by any changes in x or when x approaches any particular value. So the limit is simply equal to 3. So for this function, as x approaches infinity, the entire function basically approaches 3. Now let's look at another approach. The same question but different approaches. Lim x approaches infinity of 3x to the fourth plus 3x squared plus x minus 2 all over x to the fourth minus 1. Now, another approach basically is to examine both numerator and denominator and identify the term with the highest power of the variable x. In either case, the highest power of x is 4. So the term with the highest power, of course, is 3x to the fourth in the numerator, x to the fourth in the denominator. So what we can then do is to actually divide both numerator and denominator by x to the fourth, the highest power of x. So whatever we do to the numerator, we must also do to the denominator to ensure the function maintains the same functionality or the same value. So dividing both numerator and denominator by x to the fourth, this gives us lim x approaches infinity. Dividing this by x to the fourth, now let me write it out. We get 3x to the fourth over x to the fourth plus 3x squared over x to the fourth plus x over x to the fourth minus 2 over x to the fourth all over x to the fourth divided by x to the fourth minus 1 over x to the fourth. Now x to the fourth divided by x to the fourth, these two will actually cancel. So we're left with lim x approaches infinity. So x to the fourth will cancel to give us, well, 3x squared divided by x to the fourth. Then this basically will cancel to give us x squared. So that's squared. Right? Similarly, x to the fourth, that will cancel to give us 1 over x cubed. And in the denominator as well, x to the fourth will cancel x to the fourth to leave us with 1. So, of course, yeah, these cancel as well to leave a 3. So, it gives us 3 plus 3 over x squared plus 1 over x cubed minus 2 over x to the fourth. And this is all over 1 minus 1 over x to the fourth. Now think about it. As x gets very large, approaches infinity, any fraction with x in the denominator will get very small, approaching 0. So therefore, as x approaches infinity, this fraction, 3 over x squared, approaches 0, so does 1 over x cubed, so does 2 over x to the fourth, and so does 1 over x to the fourth. So this becomes 3 plus 0 minus 0 over 1 minus 0, which is simply equal to 3 over 1, which is equal to 3. So using another approach, the limit is the same as what we did before. So as x approaches infinity, this function approaches 3. So that is part A of the question. We'll move on to part B. So part B says, we're to consider the following piecewise defined function, f of x equals root of 6x minus 2, where x is less than 1, f of x equals 1, where x is equal to 1, f of x equals x squared plus 1 for x greater than 1, and we want to determine if the function is continuous at x equals 1. So let's write down the function again. We have f of x is equal to, f of x equals root 6x minus 2 for x less than 1. It is equal to 1 for x equal to 1, and it is equal to x squared plus 1 for x greater than 1. So essentially what we're being asked is f of x continuous at x equals 1. So how do we answer that question? Now before we start to answer the question directly, let's recall what exactly it means for a function to be continuous at a particular value of x, say e. So basically, for function f of x to be continuous at x equals a, then this is a condition which must be satisfied. Lim of f of x as x approaches a must be equal to f of a. So for the function to be continuous at some value of x, a, the limit of the function as x approaches a must be equal to f of a. Now, first, looking at this requirement, first of all, f of a. For the function to be continuous, f of a must exist. In other words, the function must be defined at x equals a. Now in this particular case, we want to check if the function is indeed continuous at x equals 1. So the first question we ask is f of 1 defined? Or is f of x defined at x equals 1? And if so, what is the value? Clearly from the rule of the function, f of x is equal to 1 when x equals 1. And therefore this means that f of 1 is equal to 1. So we see that f of x is equal to 1 when x is equal to 1, which therefore tells us that f of 1 is equal to 1. The next thing we must do is to actually find the limit of the function as x approaches 1, which means that basically we must examine the left-hand limit and we must also examine the right-hand limit and see if those are equal and if they're actually equal to 1. So we want to examine the left-hand limit of f of x. So lim approaches 1 from the left of f of x. Now let's examine the function and look at the domains. The domains are given as x less than 1, x equal to 1, x greater than 1. If we're interested in evaluating the left-hand limit, that is as x approaches, well, left-hand limit as x approaches 1, then it means that basically what we want is the part of the function where we approach 1 from values of x which are less than 1. That is basically where x is less than 1. So for this part, we will use the rule. So that is lim x approaches 1 from the left of root of 6x minus 2. And this we can complete by doing direct substitution. So this gives us root of 6 minus 2, what is equal to root of 4, what is equal to 2. Now, do we need to go any further? The actual answer is no. Why? Because clearly the limit of f of x as x approaches 1 from the left is equal to 2, which is not equal to 1. And even if the limit exists, it simply will not be equal to f of 1, and therefore the function will not be continuous. But let's proceed to find the right-hand limit as well. So the right-hand limit is when we approach 1 from the right of f of x. Approaching 1 from the right, the rule for the function is x squared plus 1, because this is governed by values of x which are greater than 1. So this gives us lim x approaches 1 from the right of x squared plus 1, which of course you can complete by direct substitution. And this gives us 1 squared plus 1, which is equal to 2. So the left-hand limit is equal to the right-hand limit, and therefore this means the limit exists. So therefore we say that lim x approaches 1 of f of x is equal to 2. But remember, f of 1 is equal to 1, so this is not equal to f of 1. This is not equal to f of 1, and therefore f of x is not continuous at x equals 1. As we said before, we didn't need to go any further than the left-hand limit, because clearly the left-hand limit is equal to 2. F of 1 is equal to 1, and these two are not the same, so therefore the function can never be continuous at x equals 1. So however, we did evaluate the right-hand limit, which basically shows that the limit exists at x equals 1 but is not equal to f of 1, and therefore the function is not continuous at x equals 1. So we'll now look at part C. Part C wants us to differentiate f of x equals x squared plus 1 from first principles. So we have f of x is equal to x squared plus 1. Now, when it comes to differentiating from first principles, for any function y equals f of x, then dy by dx is equal to lim as h approaches 0 f of x plus h minus f of x all over h. That is how we differentiate a function from first principles. So in this particular case, the function is x squared plus 1. So f of x is equal to x squared plus 1. F of x plus h. To obtain f of x plus h, we basically replace x in f of x with x plus h. So this becomes x plus h squared plus 1. We'll expand the brackets, and this expanded gives us x squared plus 2hx plus h squared plus 1. And you can verify that by expanding, right? So f of x plus h gives us this. So let's work out the numerator. We have f of x plus h minus f of x, and this would be equal to x squared plus 2hx plus h squared minus 1, sorry, plus 1 rather, and this would be minus x squared plus 1, which gives us x squared plus 2hx plus h squared plus 1 minus x squared minus 1. So what does that mean? It means that the x squared terms will cancel. So these terms will cancel, and the 1's will also cancel, and so we're left with 2hx plus h squared. And so this becomes lim as x approaches, sorry, not x, but h rather, h approaches 0 of 2hx plus h squared all over h. Dividing through by h, we get lim h approaches 0 of 2x plus h. And as h approaches 0, this of course approaches 0, so this gives us 2x. And therefore, dy by dx is equal to 2x. So when you differentiate x squared plus 1 from first principles, it is equal to 2x. And of course, if we were to apply the regular rules of differentiation, right, if we were to do this, say y is equal to x squared plus 1, then by the rules of differentiation, when differentiating a power of x, we basically bring the 2 down, multiply by it, reduce the power by 1. And when differentiate a constant, that gives us 0. So this is basically equal to 2 times x to the 1 plus 0, which is simply equal to 2x. So this verifies that our result from differentiation from first principles is indeed correct. So this was question 4, which basically wanted us to evaluate certain limits as x approaches -1, 4, and infinity, and to check a function if it's continuous at a particular value of x, and also to differentiate from first principles. Again, I must encourage you to like and share the video, and of course subscribe to the channel.